Hello, this is video 16. I'm going to go over projectile motion basics. So discuss what are projectile motion problems and how do we go about them. In this video, there are not going to be any major examples, just setting you up so that you are able to solve problems. So what is projectile motion? As you see in this picture, you have someone who's throwing a ball. This is a perfect example of projectile motion because the object is only under the influence of the acceleration due to gravity. As soon as the ball is released, that's the only thing that's affecting it, that's causing it to fall down, is gravity. We ignore air resistance, wind, anything like that. So this is an ideal situation, but it does represent a lot of motion that we see. So one of the most important things about projectile motion is that the x and y components of the motion are independent. As you see in this picture, there's a ball that is released horizontally, say rolled off from a table here, and then you see the path, which is half of a parabola. This is the path of this ball in projectile motion. What you also see are the x and y directions separated. So every second, you see the position of the ball in the x direction, and what you notice is that it travels the same distance every second. This is because in the x direction, there is no acceleration. There's no force or anything that would cause the ball to speed up or slow down in the x direction. However, in the y direction, you can see this looks like a free fall problem. Every second, the ball travels more and more distance because it's accelerating with the acceleration due to gravity at negative 9.8 meters per second squared. So the x motion is not affected by the y motion and vice versa. And when you combine the x and y motion, then you can see, for example, for these two red balls here, they combine to create this motion. And likewise for the rest of the pictures. So the fact that in the x direction there's no acceleration and that in the y direction there is some acceleration, those things are totally independent from each other. The key to solving projectile motion problems is to use the kinematic equations separately. So projectile motion qualifies for using the kinematic equations because they have constant acceleration. X direction, the acceleration is 0, that's a constant number. The y direction, the acceleration is negative 9.8. That's also a constant number. So in the x direction, since the acceleration is 0, that means if we use the kinematic equations, we can actually cross out all of those terms because they're 0. This means that the second equation is really going to be the only useful one. The first and third equations, all they tell us is that the initial velocity is equal to the final velocity, which we already knew because there's no acceleration. The velocity in the x direction remains constant. We saw this in the picture in the previous slide. In the y direction, we're often going to use the second equation as well, but it is possible to use the first or third equations depending on what we're looking for and what we're given. I have a your turn problem here, and this is one of the only your turn problems that I'm actually not going to give you the answer for in this video because I really want you to watch this other video. It only takes a minute, and all it is a demonstration done at MIT that shows this example here that you're driving down the highway. In the case of the video, they have a little car on a track. You throw a ball straight upward through the open sunroof. Where does the ball land if you consider this to be projectile motion by ignoring air resistance and anything else? And in the video, you can see exactly where the ball lands. I really want you to get that visual, and then we can come back later and we can explain what you saw. And just because now is later, let me go ahead and explain what you saw without circling one of the answers. But what you see is that if you have the ball that is thrown up vertically, but it's in a car that is moving horizontally, well, when it's thrown up, when it's still in the car, it has the same exact horizontal velocity as the car. So, after it follows its parabolic path because of its x and y components, well, where is it going to land? Well, it always has the same horizontal velocity as the car because there's no acceleration in the x direction. So that should give you a very good idea of where it's going to land. The last thing I want to do in this video is give you a few steps on how do we approach projectile motion problems. The key is to separate the x and y directions. In the x direction, you're going to try to identify 2 out of the 3 variables. When we did kinematic equation and free fall problems, I said identify 3 out of the 5 variables. The 5 variables were delta x, v initial x, v final x, a, and t. Well, in this case, we only have to identify 2 out of 3 because we already know that the acceleration is 0. So we only need 2 more variables. Most of the time, we don't need the final velocity in the x direction. And if we do, we already know it's the same as the initial. So you really want to identify 2 out of these 3, delta x, v initial x, and t. And then use the following kinematic equation to solve for the unknown. This is assuming that you have 2 out of the 3 variables. If you don't, you go ahead and look at the y direction. Identify 2 out of the 3 variables in the y direction, delta y, v initial y, and t. This is again because you already know the acceleration in the y direction is negative 9.8 meters per second squared. And most of the time you're going to use that second kinematic equation, delta y is v initial yt plus 1/2 ayt squared, although it is possible to use some of the other ones. But most of the time, you'll have 2 of these variables, let's say delta y and v initial y, and then you can use this equation to solve for time. And once you have solved for time, then you can use that time that you found and you can use it in the x direction. And this is because, as I have written in the note here, time is the same for both components of the motion. If you think about it, if you've got projectile motion and say a ball thrown up here, and you care about what happens when the ball is here. When the ball is at this location, it has traveled a certain distance, delta x. In that amount of time that it traveled this far, well, look how high it traveled that high. So you can see that this delta x, the time that it takes to travel, is the same time that it takes to travel this delta y. So a lot of times you're going to solve for time in one direction and use that time for the other direction. So that's all I have for this video. So just to recap, when you're solving projectile motion problems, you're really going to treat it as 2 one-dimensional problems that you're going to solve separately, and then you can put them together if you need to by using the time, which is common to both directions.